Hey everyone, thank you for joining us today. This is the Marche Engine Start products presentation. Today we'll be going over chargers, hybrid supercapacitors, and other complementary products to accommodate a whole solution for your engine start market. I am Roberto Regalado. I'm the International Market Development Manager here at Marche and also an EGSA member. To my right, Richard.
I'm an R&D and design specialist and we're also involved with strategic business development. I work with the IEEE as the ESSB DCRS chair and the P2685 chair.
Great, thank you, Rich. So today we're going to go over just a quick overview of the agenda that we're going to be talking about. We're going to go over the engine start system as a whole and some of the key components and how you can apply it to the rest of your application. Go over some of the engine starting chargers themselves, your ESCR, USC, LMES Pro, the hybrid supercapacitor, which we are very excited about, and some battery testers and a redundant battery selector that we can wrap up this whole solution into. And we'll finish up with some of the other applications and some case studies where I have been successful in the past.
Thank you, Bobby. So I'm going to open up with talking a little bit about engine start systems in general. So this particular image came from Caterpillar. It kind of shows a very complicated system. There's a lot involved to think about when you're implementing an engine start system. There's ventilation, power distribution, all kind of things. But what we're going to focus on today primarily is just going to be the battery charger and the battery portion of the system. Here's a typical generator. This one in particular would be approximately 1000 kVA. So looking at some of the parts here, and again, I don't want to get too much involved in the rest of the generator itself, but it's a good idea to be able to identify some of the major parts, such as the radiator, intercooler, the diesel engine, turbos on the exhaust. This portion is the generator, which is actually an alternator, and most popular in this market segment would be a 4-pole that would be operating at 1800 RPM. The HMI, which is the human-machine interface, this is where the engine controller is. Very popular in today's generators. It would have a Modbus as well as a CAN SAE J1939 interface. This would be the largest portion of the standing load on the DC system. In fact, older generator systems that have some basic analog controls, there's almost no DC drain on the charger and the battery system. We're going to talk in particular a little bit about the engine starter, as that is one of the key components in how the DC system performs. So let's look at the total DC system. Starting with a USC battery charger. What would be typical in this class would be 2 series, 2 parallel 8D batteries. Each one of these are 1400 co-cranking amps. When you wire them in series, the co-cranking amp stays the same, but the voltage grows to 24 volts. But being that there's 2 in parallel, now we have a 24 volt system that's capable of 2800 co-cranking amps. Like I said, that'd be typical for a generator approximately this size. So this DC bus, almost exclusively in the marketplace, this will be a negative ground system. In this size class of generator, you may have a redundant starter. This is kind of close to the borderline. Quite often there may or may not be an engine alternator for battery charging, and that would also be tied to the bus if it's there as well. So looking closer at the engine starting system and focusing on the starter, you can kind of see from the graphic over here, as the solenoid up on top is being energized, it closes the contacts over here, which allows current to flow to the winding on the motor. So also you notice this cantilever lever. So as the contactor pulls in, it is drawing the motor such that the pinion can engage the flywheel, and that's what actually spins the engine over in order to build compression in order to get the engine started. This is no different than the starter inside your average automobile. It's only bigger. So looking at this, we're going to talk a little bit about how the current draw and as well as the voltage fluctuation on the DC bus relative to engine starting. You're going to hear us talk about this term from NFPA 110 called 315s. So in NFPA 110, and looking at a level 1 system, and taking an example system of, like 1,000 kVA, that'd be approximately a 30-liter generator. NFPA 110 will ask that when sizing the battery, that it is capable of producing 15-second cranks that also have 15 seconds of rest in between. So what that means is that the battery must have sufficient energy to be able to accomplish that many cranks, but it also must have sufficient power in order to deliver the starting current. So let's look at this in terms of breakaway current. So again, the image up on top, that is the starter current, how much current it's drawing from the battery. And as we all know, Ohm's law, due to internal resistance and losses on the battery, as you start pulling a lot of current through, it's going to give you an instantaneous voltage drop. So that's kind of why the voltage is kind of a reflection of the load current. So this first portion over here is called the breakaway current. You'll notice that it's a fast rising edge, and in this instance, it gets to over 1,400 amps. And it's very narrow. Typically, this is there and gone in less than 700 milliseconds. So what constitutes this high leading edge is building flux in the motor and overcoming the beginning inertia of turning over that engine. So you'll notice when there's a high spike of current, again, there's a large momentary dip in the voltage on the battery system. So the next portion is considered a rolling current, or some people call it cranking current. So this is while the starter is actually turning the engine, but before you've actually accomplished diesel ignition. So the controller that's inside the generator will normally limit this time to somewhere in the vicinity of 10 seconds or maybe 15 seconds. The reason that we go for 315s is because NFPA 110 is going to require that's how much energy you should have in a level 1 system. So some factors that affect this would be the engine displacement, the temperature, the oil viscosity. All these other factors affect what this rolling or cranking current will actually be. And you'll notice that there's a voltage dip during the same period of time. Again, the load voltage, or the battery voltage, I should say, is a reflection of the total load current. So here's another view of, this comes from the EGSA, and so this is while starting. The EGSA has a different recommendation for these periods. So B being the initial breakaway period, on a 24-volt system, they want to see that the battery voltage stays above 12 volts, even for that momentary dip. During the cranking section, or the rolling current section, the battery must stay above 18 volts. And as you can imagine, if we're not talking about a 12-volt DC system, or I'm sorry, not a 24, but we're talking about a 12-volt, then these voltages would be cut in half. This portion over to the right is after the engine actually starts, and you'll notice that the RPM curves up, because that's when the engine is actually getting itself going. So the engine starts, the amps drop down, volts kind of start climbing back up. So let's talk about this. What happens if your delta V, your voltage drop, is too large? Well, under certain circumstances, you might be hindering the ability to crank the engine. The EGSA only has recommendations against the cranking requirement, but your engine ECM or even the switchgear that might be operated by a larger generator could be affected by this momentary dip of voltage. So that's why it's very important that to look at sizing the system properly and also maintaining your system. Because if the cold cranking amp rating of the battery is too small, you'll have too large of a voltage dip and you could encounter a problem. If the battery internal resistance is high because it's aged or it hasn't been taken care of, you'll have excessive voltage drop and you may start to compromise these components. Same if the wire is loose or corroded. Either way, you could run into a scenario. Here's an example. Let's say if you had a momentary dip that was severe enough, you could drop out the ECM, the engine control module. And if that happens while cranking, it's going to interrupt the fuel pump, and that's going to prevent the start. And that's a bad day because now you're forced to reset on the system, and you could try over and over again and never get it started. So that's why paying attention to the total voltage drop is so important on an engine start system. So we're going to throw around these terms, such as energy and power. So I'm going to spend some time explaining this because it's going to come up again later in our presentation. So let's look at two batteries. Well, you say, Rich, these are buckets. Well, they're the same as a battery. Guess what? So these have the same amp hour rating because they're the same size bucket, they have the same volume of fluid. They have the same voltage because they have the same atmospheric pressure and we're in the same gravity. So what makes them different? The one on the left has a low cold cranking amp rating, the one on the right has a high cold cranking amp rating. So the reason for that is because, as you can all imagine, with a larger pipe, larger valve, the rate at which water can flow, in terms of water flow per second, you can flow a lot more water. You can empty this bucket much quicker. This means that there's less resistance to the flow of water. So same thing as a battery. When there's lower internal resistance of the battery, you have less impeding the flow of current, so you'll have less voltage drop on the battery. So batteries that you'll find specifically for engine start have less internal resistance, which gives them a higher cold cranking rating than for a given amp hour, as opposed to a long duration battery. So let's look at where we have the same power, but different energy. So again, we go back to our bucket analogy. The amp hour rating is different because the volume of fluid is different. The one with the larger volume has a larger amp hour rating. You have more available water in the bucket. So they have the same voltage because the atmospheric pressure and the gravity is the same, but the current flow, because this pipe has the same resistance, it will limit the volume of water in terms of flow per second. And I know you say, well, wow, Rich, is current really a rate such as a quantity per second? Well, absolutely, because an ampere is related to coulombs per second. So it really is a rate. So keep this in mind, the analogy of discussing power versus energy. Later on in the presentation, we'll bring it up again when we talk about the HCAP versus Supercap. So let's talk a little bit about batteries for the system. What's far and away most common in this market segment is a lead acid battery. I got PB here for the lead. So the lead acid battery, it's rated in cold cranking amps, but typically not associated with an amp hour rating. So that can cause some confusion. They're normally in a BCI group size, similar to the batteries that are under the hood of your car. Those are all different group sizes. So what they don't give you in this market is independent sizing in terms of how many cold cranking amps you generally need for an application. So let's look at this in terms of the other battery, NiCad. So if you really look at these, they're polar opposites of each other. The lead is rated in cold cranking, but not in amp hour, yet on the NiCads, it's just the opposite. It's rated in amp hours and not cold cranking amps. These are grouped together in a monoblock. These are normally 1.2 volt individual jars. There's no sizing guidance for the lead, but there is a lot of sizing guidance from other standards such as IEEE 1115 from SAFT, ALCAD, HOPICA. A lot of other guys have sizing tools available. The leads will normally need to be replaced 2-3 years per NFPA, but the NiCads, they'll last a long time, 20 years, plus have a wider temperature range. But the thing with the NiCad is they're expensive and they're difficult to recycle. So a lot of people went out with the lead acid battery because they're cheap and they're easy to replace. And when we say recyclable, lead acid battery is actually 99% recyclable. So let's look at sizing a system. On a lead acid battery, again, they're generally sized and rated in cold cranking amps, not rated in amp hours. So cold cranking amps, you should be thinking, is synonymous with power, and amp hour rating, how much water is in the bucket, is synonymous with how much energy is available. So engine starts, they really don't consume a lot of amp hours. In fact, we went to go test a larger 50-liter diesel engine system that was 1500 kVA. It really only consumed about 6 amp hours. I mean, we're not talking a lot of energy. What we need is power. So quite often, 2 parallel strings are used to meet the cranking ampacity, and they're not really sized in for redundancy. They're really designed in for design margin. So the typical battery sizing that we would use in other stationary markets, such as in utilities, substations, oil gas applications, well, those are energy applications, so those are sized in amp hours, and you would normally go through this formula. This is how the Marche sizes, according to IEEE 946. But because you don't have an amp hour rating, you really can't use this system. So cold cranking is a really nice system because it gives you the worst case cranking performance of a new battery. The battery that you choose and select for the system must meet or exceed the generator's requirements. You really can't have too large of a cold cranking amp rating on an engine start application. So let's look at that. Cold cranking amps. So as defined by the SAE, it's the amount of current that a 12-volt battery can deliver at 0 degrees Fahrenheit for 30 seconds while maintaining at least 7.2 volts on the terminals. And by the way, this battery has been saturated at 0 degrees Fahrenheit for at least 24 hours ahead of the test. So this allows you to put on a very heavy load. This really tells you how the battery is going to perform when it's cold and when it's being stressed with a high dynamic current, such as starting the engine. So let's look at totally sizing up a system. So I took a snip from a 1250 kVA generator, and you can ask around for some independent advice, and here's what one old timer gave me. He said, select the smallest battery by cold cranking amps that meets the generator spec. So looking at this, they're asking for 2, which actually is 2 in series, because the 12 volt BCI batteries, well, they're 12 volts, and this is a 24 volt system. So they want 1100 cold cranking amps, and they want it to be an AGM. So we look up on our data sheet and we find, lo and behold, here's a 4D battery that meets the cranking requirement. So after you've done step 1, you go to step 2 and say use 2 parallel strings. That gives you, it's not so much for redundancy, but it's there to help cover other terms like battery aging, the manufacturing tolerance from one battery to another, possibly operating lower than 0 degrees Fahrenheit, adjustments for altitude or other engineering margins. So this is really one of the reasons that you end up seeing 2 parallel strings. So now that we've sized the battery, how do we work on the charger? So UL 1236, here's a snippet, I just love this one. Within UL, they want you to be able to recharge the battery to 100% of the battery's amp hour rating within 24 hours. But the problem is, the batteries in this market segment, they're not rated in amp hours. You gotta follow the standards anyways. NFPA 110, they say something kind of similar, but level 1 recharge, they want 100% returned in 24 hours. Or if it's a level 2 application, you can use a smaller charger that would return it in 36 hours. But although NFPA 110 doesn't specify amp hours, they imply that they want 100% restored. So working with the IEEE, there's a chart that we can make here that correlates the minimum charger size in amps on the left column versus the cold cranking amp rating on the right. And it's not a direct perfect correlation. This is just one of those tables that was assembled from some available tests on a lot of available batteries. So if you have a standing load, you should add that to the result here. So let's go through an example. Let's say I want 2 parallel 850 co-cranking amp AGM battery strings that has a 3 amp standing load. So I would first look up and say, well, 850 amps, that's right over here. That gets me to a 7 amp charger. So I've got 2 of them, so I need 14 amp charger. So then I have to add my 3 amp standing load, so we get 17 amps. Well, we don't have a 17 amp charger available, so we round up to 20 amps. So data on this table was sourced from the draft version of IEEE P2685, which is the recommended practice for energy storage for stationary engine starting systems. And next, we're going to have Bobby come up and talk about engine start products.
Okay, thank you, Rich. Very interesting conversation that you just went over. I just want to reiterate that the importance of that table and sizing your battery and how to size your battery charger. We continuously get that question here at Marche. What size generator they have, what size cranking CCA battery they have, and how do they correlate that to their charger. So very interesting table. If anybody else has questions, go ahead and please contact us and we can help you out further as needed. So I'm going to continue on to the engine starting products themselves. I'm going to go ahead and start and show you guys really the brochure that kicked this off. Really just to focus on solution as a whole, on different products including your battery chargers, different types of battery testers, supercaps or hybrid supercapacitors, batteries, and then redundant battery selectors. Moving to the actual engine starting products themselves, here you have a nice graphic actually showing you different or typical locations. Obviously this is not the only situation that they would look at. You can actually move them or different types of orientations depending on the actual generator setup. Here you can see the LMES Pro is actually situated on a much right directly onto the actual generator itself, where you can actually have it mounted on the wall, across the wall, or in a different area depending on your layout. Obviously smaller sites will have a much more restrictions, and then obviously bigger setups will have much more available as far as adding redundant battery selectors or more batteries or different setups. Let's start with the ESCR. I want to start by mentioning that with this ESCR, this is an SCR based technology. Marche still offers very many other technologies in regards to chargers, but I will focus on some of the more popular technologies and some of the more popular models as far as what the market is currently looking at this moment. The ESCR, just a few subtle distinctions or characteristics of it. It's still a microprocessor controlled SCR technology, and it's got a 12 or 24 volt output selection, which is field selectable, so you can actually go ahead and do it through the menu structure here. There's no need for any types of dip switches or mechanical changes to it. So ultimately what that gives you is hopefully you have less models you need to stock out in the field. You also have an automatic AC range selection with our wide range PFC, digital flow and equalize adjustments, battery fault detections, and you're still meeting NFPA 110 and ANSI requirements as far as surge, all within a 5-year warranty, and again a UL 1236 package. just some changes or some actual differences in regards to the ESCR versus our ESCR V2. You're going to have updated characteristics in form of conformal coating. You can see here that we have updated some of the ruggedness of the actual unit itself to have conformal coating. What it does is it improves from humidity, any type of harsh environments, salt-laden environments. Battery test feature was added just to give you that connection or that testing capability when connecting from a battery charger to your battery, or show if there is any loose connections from one point or another. A snubber circuit to improve the reliability and surge protection. An anodized heatsink assembly. What this does is gives you a no fan operation option, so it will be completely convection cooled. A high voltage shutdown feature to protect the battery and the charger itself, and then higher performance components to give you higher ratings as far as voltage and temperature. Moving on to the LMES Pro, to show you here the ideal point of installation, or a point of installation, as it is relatively small and discreet. As you can see, thank you Rich, the LMES Pro. This is actually also a high frequency microprocessor controlled battery charger. It was developed specifically for use in lead acid, NiCad, and supercapacitor technology. Again, this unit is also conformal coated to give it that rugged protection from other harsh environments or humidity. And it's also in an IP32 enclosure, so it does give you that protection as far as water and any other type of debris and whatever is involved with the environment. We do have a temperature compensation or an internal temp probe to compensate the voltage if there is either too hot or too cold. And we do have the option of adding in external temperature probes. So this would be ideal if you were to put it on your battery terminals themselves. This is also convection cooled. As you can see, there is no heatsink, there is no fans, but you can see in the back there is a heatsink to help with the cooling of this device. This is a single phase. This is available in 12 and 24 volt. Single phase input, 102 to 264 VAC with a 2-year warranty, and UL currently pending. So why the LMES Pro? As you can see here, we have a nice little image of the front itself. As you can see, you have some very defined connections as far as your inputs, your outputs, your temperature sensor connections, and these config switches here is what would actually allow you to change your voltage as far as 12, 24 volts, or different voltage ranges for your lead acid, NiCad, and supercap configurations. So the LMES Pro is IP32 rated enclosure. That's one of the big factors in pushing the LMES Pro. Another one being that it comes standard with Modbus RTU communication. As an option, or to improve on that Modbus communication, we also have a J1939 that'll be available within the same port. As you see here, this would be utilizing the same port, the COM port for RTU or J1939. Obviously, one has an option to add that J1939 connection. This is a little bit more of a standard, I guess, feature nowadays in the engine starting market. There is a lot of diesel engines that are running off of J1939. There is also a 4-stage battery charging algorithm on this charger. What it does, it gives you the bulk stage here. As you can see, you get a constant current where you have that lower voltage, or you're starting to charge your battery. And when you come up to a voltage or a flow voltage, you then go into the absorption rate or your equalize rate, depending on the configuration. You will then, at that time of your equalizer absorption, move into your float. As you can see, obviously your current has already dropped down into a trickle current or a flow current. And then stage 4 is where you would go into your second equalized stage as well. Anything different? Moving to our USC product. As you can see here, this one in the middle, This is also a high frequency charger. It's probably one of our more popular brands or most popular products at the moment for the engine starting market. Some of the options or some of the features it has is a microprocessor controlled technology again, as it is a more common technology in the field. But this is also developed for lead acid, NiCad, supercapacitors, and also lithium ion or LiFePO4 batteries as well. So we're very excited about that. We're actually one of the few to actually have all of the charging technologies being able to be charged with one unit itself without it being any type of other options as well. Again, it is conformal coated. There is that protection that is required or it's important to us. You do have the temperature compensation internal with your external option. It is fan cooled, so what this does is with the fan cooled design, it does allow you to have a much smaller, lightweight package. Very important, especially out in the market where there is competition or other brands have a tighter space or area that this needs to be installed in. And it does give you a wide range of sizes as far as your current ratings as well. So why the USC? The USC has a 3-stage deep discharge battery algorithm to really protect the batteries and the charger itself. There is no mechanical adjustments required on this, so everything you would see is done through the front display, and I'll go through some of the menu adjustments in a moment. But it does operate from a -40 to 65 Celsius, and there is a D rating once you do exceed this point all the way up to 70 C as well. It comes standard with Form C contacts, charger failure, AC failure, low DC voltage, and high DC voltage. Adjustable charger profiles, Supercap mode, LiFePO4 mode, and your Modbus communications RTU, and your optional TCP IP connection. I'll save this point for last. I'm going to go ahead and show you guys an actual method of changing, or how easy it is to actually change your battery modes. So here you go ahead and just enter your menu structure. You actually have a few different settings. Battery type, we'll go into the battery type. At this moment it is in ultra cap mode. So I'll go ahead and adjust it for a lead acid mode, and you can actually go ahead and see that voltage adjustments as a standard. So you saw that it changed from actually 25 volts all the way to a 26 volt setting, which is different adjustment ranges that are set as default from the factory. But going a step further, you can also see that there is how easy it is to go ahead and adjust your flow voltage setting up and down. So you had it set at 26.1 and easily go down to, for example, a 25 volt level. So just some rundown on how easy it is to actually set this unit in the field and what it takes to really, do the other changes as far as the charger profiles. Going into the charger profiles that I mentioned just a moment ago, the LiFePO4 profile, which is lithium iron phosphate. As you can see here, you still have your same stage 1, which is your bulk stage, and then you do have your once you reach that higher voltage level, you do still remain in that voltage level. I guess your float level you would indicate it as, where your current starts to taper off much quicker and much faster. I have seen other instances where this is actually done within a few, maybe 15 minutes instead of 3 hours, but again, this is definitely dependent on the size of your charger and your battery as well. Moving into your stage 3, once you do get down to that trickle charge, because it is a lithium ion phosphate battery, you do not have to require any type of trickle charging or any floating at this point. So at stage 3, you would actually end your charging, and then we would have a stage 4 charging, where if it would sense a voltage dip, then you would go ahead and turn it back on and top off the battery. Going into a supercap profile here on the right side, You can see a constant current again, so you do have almost a similar stage one as you would with the lithium iron phosphate battery, where you get that constant current here, as you see the dotted green line, where you get to a constant voltage at a certain point. You would then at the end of this stage drop down into a where your current again would taper off, and you would have just a standing flow current to maintain your supercap. Now, another very important feature that we do have as a standard on the USE is going to be the Modbus J1939. This is actually now, as I mentioned, a standard feature. It's very important to us, or to keep up with the industry, as we are seeing most diesel generators now run on this protocol, which is CAN SAE J1939. This is much easier as far as diagnostics and communication back and forth with your charger, your control panel, your generator panel, and other components on site which run off the same protocol. Some of the settings that you can actually monitor and adjust with the J1939 option on the USE are going to be DC output voltage, DC output current, alarms, and charger modes. You can go ahead and change some set points as far as the mode, high voltage alarm, and low voltage alarm. Quick overview or quick summary of our engine starting chargers, primarily being the LMES Pro and the USC battery charger. You have the LMES Pro on one hand being the most cost-effective solution and typically being designed for an OEM opportunity because of its low cost and really standard offerings and features that it has. You do have the LED indicators, and it is set up, or you can set it up for 12 or 24 volt applications, all in the same package. Compared to the USC, where you do have much more competitive sizes as far as voltage and amp, so you can actually go with a 12, 24 volt. We actually do have some more voltage ranges allowed, obviously not for the engine starting market, but we do offer a much higher range of amperage sizes. Obviously, the big factor for the USC is that you can actually charge much more than just your lead acid and NiCad. You can charge lithium-ion batteries and your supercaps with all adjustable profiles. And your standard Modbus J1939 feature is very important to us. Again, we have to reiterate that. Along with other extensive protection features, just a quick rundown of some of the protection features being fuse and surge protection, AC over voltage protection, thermal protection, blocking diode, short circuit design protection, and then a cranking disconnect feature would allow the charger to disconnect itself from the system once you are cranking and you have a very deeply discharged battery. Okay, onto the H-caps. I'm going to go ahead and let Rich take over as well.
Okay, thank you, Roberto. It was really exciting to hear about the LMES Pro and the USC battery chargers and how they're able to both adapt to the new H-caps as well. There's one more feature of the USC that I'd like to remind our folks about, is that we now have the ability to, with a special option, to size this for a 277 volt AC input.
Thank you, Rich. Completely forgot about that.
No worries. So, on the H-caps. What is an H-cap? Well, an H-cap is an asymmetric, hybrid, lithium-ion supercapacitor. And I know that sounds like a mouthful, but part of what that entails is that on a traditional supercapacitor, I'll call it a legacy supercapacitor, they store energy as an electrostatic field on the plates of the supercap, and there's really no chemical reaction there. It's only electrostatic energy storage, and that's both a strong point and a weak point for a traditional or a legacy supercapacitor. So let's talk about these legacy supercaps. They're really neat because they have a very long life. you should be able to expect more than 10 years out of it, more than 1,000,000 cycles at wide temperature range. One thing that they're really known for is that they've got tons of power available, but sadly sometimes not enough energy. So the power is really useful in an engine starting application because this is what produces the breakaway and the rolling current, is good power capability. But their biggest problem is that they generally can't sustain 3/15s of engine cranking, because once you get past 2 or 3 attempts, you run out of energy because there's not enough energy in the traditional EDLC supercapacitor. So quite often these systems rely on a lead acid battery being paralleled with the supercapacitor in order to meet the energy requirement. These also have a high self-discharge. You can disconnect it, and sometimes within days you'll need to completely recharge the supercap. So a hybrid supercap, or an H-cap from Marche. This is unique. It's also a long life product. But you'll have a little bit less cycles out of it, but we're still talking 100,000 cycles in a typical application. And before you get intimidated by that number, keep in mind a lead acid battery is about 400 cycles. We're operating at 100,000 cycles. We have a much wider temperature range, 10 to 20 times more energy available than a legacy supercap. We produce, we still have enough power to produce breakaway and rolling currents, and we can easily sustain 4/15s. We actually went up to Wisconsin and ran a test in a freezing environment on a cold engine on an H-cap that was charged 2 days before, and still had no problem after several days of sitting without charge on the H-cap in a cold environment, getting 4/15s out of it. So we have no problem at all with energy. And our H-cap also has low self-discharge, and that's in part because of the asymmetric structure. So we put together this Ragone plot, so that way we can kind of discuss some of the differences between batteries, asymmetric supercaps such as our H-cap, and the legacy EDLC linear supercaps. So on the vertical scale, we're talking about specific energy. So that's how much energy is available in the box for a given size. And batteries, they're going to win in this category. For a given volume, you'll have more energy available in a given volume than a supercap product. However, let's look at the x-axis and how that relates. So let's look at recharge time per unit of stored energy. Well, the EDLCs recharge the quickest, the batteries recharge the slowest, and the H-caps are kind of a hybrid in the middle. Where if we look at in terms of cycle life application, if you have tons of very, very frequent cycles, EDLC kind of fits, but a lead acid battery does not. The asymmetric hybrid, it kind of crosses this boundary where you can get quite a bit of cycling performance out of it. And it's similar to a lead acid battery where you can increase the cycle life by using shallow discharges. You can have the same kind of improvements on an asymmetric lithium-ion supercap such as our H-cap. Also, in terms of energy versus power, the EDLC, it's going to win the power density, where lead acid batteries is not. And the asymmetric supercap, it kind of falls in the middle. So let's take a look at an application where we actually, like I said, we went up to Wisconsin and tested a generator. This one in particular, it was 1500 kVA on a 50-liter engine. So this would have been started with 4 8D original lead acid batteries, and you can kind of see the test that we ran with using only 2 H-caps. Even though we would recommend 3 in this application, we tested it with 2. You can see how much smaller the H-caps are than the total footprint of the lead acid batteries. So let's take another comparison of this. So the lead acid batteries, these are 125 to 130 pounds a piece. That means someone has to move 500 pounds worth of batteries, and per NFPA, replace them every 2 to 3 years. Well, on the HCAP system, so much smaller, this one module that's being highlighted, that is 24-volt modules. I don't even need to series connect them. I just need to parallel as many as what's needed to meet the cranking and the energy requirement. So this is in a group 31 size case. These are only, they're under 50 pounds each. So keep in mind that on the lead acid battery, with that weight of 125, 130 pounds, OSHA is going to require 2 people to move those batteries. And as you can see in the previous picture, there's not a lot of room for 2 guys to fit in here and actually replace batteries. So it's very easy for one technician to be able to install these. When looking at the total cost of ownership, you'll have easily at least a 50% cost savings over the life of the product, only 10% of the weight, less than half the space, and 0 maintenance as compared to a lead acid battery.
So Rich, I want to point out that this is an actual Supercap itself. As you can see, I was lifting it myself here. This is a real life Supercap. It's not a dummy cell, so this is what you would see in an actual application itself, and how light it is for just one technician to take 1 or 2 of these to the site, install, or even have one actively in their truck, just as a backup itself.
Absolutely, and it has these real nifty brass combination terminals that have 3/8 post as well as an SAE type clamp connection that's available. So this is very easy to install and adaptable to almost any type of situation. Let's look at legacy EDLCs. Why not just parallel a whole bunch of them in order to meet the energy requirement, in order to meet NFPA 315s of cranking? So you could do that. It's possible, I guess, but let's take the same generator. Looking at an example that is a 50-liter engine, you're going to require approximately 30 EDLCs in order to match the energy of 2 or 3 Marche HCAPs. On this particular installation, I would actually recommend 3, but still, approximately 30 EDLCs versus 3 HCAPs. That's a big difference, not only in price, but also in volume. There's nowhere to fit 30 EDLCs in that small trailer. So moving on, I'm going to hand it back to Bobby to talk about some complementary products available for the engine starting market.
Okay, thank you, Rich. Moving on to a few complementary products, we're looking at the RH battery tester. Battery tester itself, what it's going to do is going to allow you to measure battery performance during your charging or discharge cycles. So it is a 750 watt load tester, and it's available to test within ranges of 10 amps to 64 volts. So ideally your 12, 24 volt, and 48 volt battery strings. A nifty thing about this is that it does have a data logging via USB connection, so you can go ahead and actually obtain that data, pull it out, and look at it on your laptop or through an Excel file. It does have, as you can see on the image here, you do have your connections via connector from your charger to your battery tester in line, and then also your battery connection directly out as well. So it is something that you can permanently install. Obviously, it'd be better to check it as far as a trend to make sure your batteries are either going in the correct direction, or if they're trending down, obviously you know that then it's time for a replacement on your batteries, or maybe something has to be changed with your setup. Here you can see a much better image of the 4-line LCD display and what it actually will indicate when you're doing a test. So it's a lot simpler to maneuver. You do have your LED indicators to let you know if it's in progress, the test done, it failed, or if the battery is charging as well. So you can go ahead and charge your battery through this device. It's not going to harm the battery. Obviously, there is a restriction on how large you can get through the battery cabling as well. A few quick advantages of having a battery tester, or some of the ideal things you would do with this battery tester, are going to be capacity measurements, and the fact that you can do them as monitoring your voltage, your discharge current, amp hours that are put in and taken out of the battery itself under a specific load. Operating range, as I mentioned, it's 10 to 64 volts. Dual test modes, either done in constant current or constant power. Selectable test terminations being a battery end voltage, maybe in regards to protecting the battery, not getting down too low. Elapsed time or a certain duration, or maximum amp hours that was taken out of the battery itself. Different battery test cycles can be done automatically. Obviously, they can be done in your daily or your weekly, even monthly cycles. And your data logging is available through an Excel file or a CSV Excel type file, where you can easily track those changes or those trends of your charge and discharge cycles. Again, this also is a self-powered battery tester, as you are applying or connecting a charger and a battery to it. There is no external power or AC that's required to power it up, and your reverse polarity protection. Just a quick overview of what it looks like on the actual Excel file. As you can see here, you have your most important parameters being your date, time, your ID. Obviously, you can set up different batteries for this. Battery amp hours, your running cycle, your actual testing mode, charging or discharging, your set points, endpoints, voltage, currents, and all that good stuff. Just also show that quick diagram here of how easy it is to go ahead and set up a quick trend line just with those data points from that one charging or that one discharge cycle. It's very easy to go ahead and see a trend or set up, a continuous or monthly cycle to see how it keeps trending either upwards or downward in your system.
Thank you, Bobby. It's interesting to note that also on the RH3 tester that it can also test the new HCAP as well.
Of course, yes. So that last log file was actually done utilizing our HCAP as well.
Oh, that's good. Here's another product that's available for the engine start market from Marche. This is an ARBS. It's an automatic redundant battery selector, and you can see from the diagram it's a very simple product. It allows for easy paralleling of two separate banks of batteries, and really the purpose of paralleling in this instance is to add redundancy into a system. Now, on smaller generators, you're not going to be able to necessarily fit two separate DC systems, but in a larger and more important and more critical application, an ARBS certainly allows you the redundancy of having as many batteries on each bank and as large of a charger on each bank as necessary. What's great about this is because of the blocking diodes, it allows you to facilitate maintenance on the batteries. So for a very highly critical application, I would definitely recommend using an ARBS. Taking a look at a system that must be NFPA 110 compliant, technically in the NFPA 110 as written in 2019, they didn't have the vision of having an HCAP in the system. The only energy storage devices that would be allowed would be a lead acid or a NiCad battery. We've been able to utilize HCAP or even EDLCs in the past through an ARBS in a system like this. We're, in addition to participating in the EGSA and in the IEEE, we'll also be participating in the NFPA 110 and seeing if we can encourage the inclusion of hybrid supercaps based on actual test data. So really looking at La Marche overall, we have a really wide and broad scope of solutions that are available for your critical applications. whether it's the ESC battery charger, the RH tester, the ARBS redundant battery system selector, or the LMES Pro, or even the HCAP product. We have a solution for you, whether it's storing the energy, charging the energy, or sharing the energy, or even testing for the energy. Marche has a solution for you. So putting it all together, it's all available for you from Marche. If you have a critical application, come to Marche to take a look at chargers, ARBS, and HCAP systems. Next, I'd like to talk a little bit about applications. So let's look at some engine starting applications. The trailer on the left, this is a very small generator. This would typically be started with a 12 volt lead acid. That'd be very common. Whereas when you get into this larger generator on the right, we're talking about like 150 kVA. This would also be a 12 volt system with a single group 31 type of battery. So being on a trailer system like this, you might be a provider of rental energy. So these might be sitting on the parking lot for a good period of time before actually being in use. That's not a good application for an EDLC or even for some of the lead acid batteries that have higher self-discharge. But an HCAP, that has such a low self-discharge that would perfectly fit this application, even with several months of sitting idle in a parking lot waiting to be utilized. So it's a really good fit for small portable gensets. Moving on to a larger genset, in this category, you'd be something in the size of 750 to 2000 kVA. Your engine displacement in a trailer this big, you'd be talking about something in the mid 20 liters up to 70 liters of displacement. On the larger ones, you might be talking dual starters. So some of the uses for this might be large emergency backup. Think about like a Hurricane Katrina or emergency natural disaster relief. Or even if you're a utility running planned maintenance, but you have a highly critical customer that you need to support. So if you're doing something large like changing out a transformer for a utility, but you need to keep that customer going, you're going to be pulling a trailer to supply the customer. This is a perfect application for an HCAP, not only because of the low self-discharge, but also because of the energy footprint and the available power that's really available to crank and start up that engine. You'll notice that the generator only occupies normally about the front half or so of the trailer, where the rear half would normally encompass the switchgear that's used for paralleling this to either a utility grid system or to another generator system to connect to the load. So looking at the inside of a trailer like this, there's not a lot of room inside. So this is a kind of a top view, so that this would be the side walls of the trailer looking down into the generator. So there's not much room for multiple people to be changing out lead acid batteries, anything like that. And two people would be required to move a single 8D battery because they're in the vicinity of 125 to 132 pounds. So where I'm at in this picture, I'm actually sitting on the battery pad while doing HCAP testing. So in a small cramped area like this, there's not too much room for a truly redundant DC supply system. Now when you get into a larger generator application such as this might be hospitals, airports, data centers. These would be probably classified NFPA level 1. Your generators in this class might be between 1,000 to 5,000 kVA apiece, and they're likely to have redundant generators, such as in this image, that are doing redundant load sharing. So in a space like this, and here's our A12, and you can see the 8D batteries lined up on the side. Because there's so much floor space here, this is a good opportunity for redundancy because of the floor space. Speaking of floor space, Here's a similar multiple generator application. This one in particular has NiCads. And you can see that unfortunately the NiCads, they take up a lot more floor space than the equivalent engine cranking capability of the lead acid batteries. So keep that in mind as you're planning out a system. And that's really one of the reasons why NiCad is not as popular for engine starting as well. So no matter how you plan to use it, no matter what the engine start application, whether it's large or small, Marche has a solution for your most critical applications.
Awesome. Thank you, Rich. I'm going to go ahead and jump into a few success stories or some case studies that we've actually have dealt with directly with some customers this past year or so. So the first one being, again, that situation up north where we ran into a couple generators being 30 and 50 liter engines, 1 megawatt and 1.5 megawatt respectively. They ran into a situation where they had a very tight space. They were replacing these batteries regularly 2 to 3 years apart. And they were just having a little bit more difficulty with the size and having to get people up there to make sure everything was correct every single time. In this case, as you can see here, the 50 liter engine had 2 starters versus the 30 liter having only 1. Going to the solution, we actually recommended they go with the setup that Rich mentioned a little bit earlier, being 2 H-caps replacing almost, in this case, it's 2 scale almost, as you can see here in this picture, the 480 batteries they have originally. So the customer, as you can see in the area that Rich was at, was very happy to go ahead and replace these 80 batteries with the H-caps, which were much smaller, obviously just on one side. You don't need to go in there and continuously replace these batteries. We're looking at maintaining these H-caps for a 10 or maybe 10 years or maybe even longer, depending on the situation, correct? So this slide being much more important to the overall customer as for showing the capabilities of what an H-cap can do in terms of power. I mean, you do see in this case, this H-cap was cranking this engine, which was reaching, what would you say, Rich, more than about 14?
That was larger than 1,400 instantaneous amps of breakaway and over 470 amps of cranking.
Of regular rolling current, correct. So as you can see here, I know these lead acid batteries do have different CCA levels that right away you might say, well, that's going to be one of the factors, but we're able to go ahead and crank much more power, get much more power out of these H-caps than we can with these lead batteries. Not to mention the overall weight and the space that you are saving, and in the long term, how much of the cost savings you will have. And no maintenance really to go out there and have to continuously be checking these batteries or checking electrolyte levels as well. Moving on to a USC case study or story that we had a case where an OEM dealer and actually other distributors ran into a situation where they could not get a charger quick enough for firsthand. They were actually looking for very quick lead time. They were looking for various units within a week, but they also needed to meet this special 277 volt input. So we went ahead here and we standardized this voltage range and made it as a very easy or small modification to the unit. So we were able to go ahead and push this out within a few days. Not to mention that they were very happy that we were able to go ahead and make the J1939 option allowable on the unit itself, as they are interfacing with various other components and devices in their system that do work on that J1939 protocol. Aside from that, it was very easy to go ahead and actually use this USC and replace other units in the field, as it was a much smaller, retrofit, as it is smaller than a lot of other units in the field, and it's the footprint itself does not take much more room. So they were in some cases saving on space. Again, it was a short lead time, so we're able to go ahead and actually stock various of these units for them in the future, or if they do run into another situation like this again. And we are ideally priced. We are very competitive with other units in the field, and competitors that are also out there pushing similar styles, but maybe lacking in different areas as far as the voltage range, the J1939 communication, and maybe some of the protective features that I covered a little bit earlier on the USC. So I want to go over again just how Marche can provide your overall solution in terms of battery chargers, capacity devices being your HCAP batteries, lead acid, redundant complementary solutions including your ARBS, and even testing solutions with your RH battery tester as well. I want to thank everybody for taking the time to watch this video. Rich, great job on the presentation as well. And if there is any questions or comments, so please feel free to contact us at the email here at the bottom right corner. Maybe I'll take away the...
There you go.
Anything else you want to add?
And if there's any further reading or questions, questions, please feel free to contact us. But as in terms of references and further reading, here's a list available, and hope to see you guys again soon. Thank you very much for spending time with us. Bobby, Miguel, thank you so much, and enjoy, and look forward to speaking with customers about engine starting applications.
Thank you very much, Rich. Hope everyone enjoyed.